In the last part of this lecture, let's talk about how we can numerically solve partial differential equations. Essentially, we know we have a fundamental pricing PDE, and if we're able to solve that, then we'll get the price of the derivative asset. In finance, we typically will have a rectangular mesh. That's why we have we can use the finite difference method to solve the partial differential equations. Let's take a look at the, for example, the Black-Scholes Merton PDE, which is of this particular form here. And let's take a look at for put. So here we use a put as an example. The same approach can apply to obviously to a call as well, or any other ones. But let's just, for illustration, let's take a look at a put. So here, this is a partial differential equation here with a dividend yield here. So we can construct a grid of size n times m. So we have, say, we divide the time interval into n different steps, and we can divide the stock prices levels into m different intervals. So, the stock price will go from 0 to x max, some very large number, and then you divide them into m different, ones, and each delta will give you a increase of a price, and each delta t will, travels you from current time one time interval into the future. So if you look at the grid, there are actually n plus 1 times m plus 1 points here. So you can sort of draw a grid like this. So this delta S to delta S all the way to S max. And then this delta T to delta T all the way to the maturity time here. So this here is what the realized price are at maturity, okay? So by convention here, we're denoting the lower left corner 0, which means we're denoting this 0, 0 here. And the upper right hand corner will n plus 1, n plus 1. So this point here will be n plus 1, n plus 1 here as a coordinate system. Okay, so then it gives us the coordinate for which node that we talk about on this grid here. Now there are two finite difference methods we can implement. There are pros and cons. One is called the implicit finite difference. One is called the explicit finite difference. Let's take a look at each of them. In the implicit finite difference method, we approximate the derivative on the interior points as follows. So your partial derivative of df ds is then you're looking at the same time point between a value at a higher grid minus the value at the lower grid and divided by the change of s. So basically, you're looking at the f here minus the f here divided by the change of s. That gives you the change of f per change of s. Okay, but you're doing it at a particular I here, this vertically. That's called a forward way. And you can do a backward. Which means that if you want to get a the change, the partial derivative here at the point ij, you are looking at, let's say this is ij, then you're looking at this value fij minus fij minus 1, and that divided by delta s. So that give you the backward way. But then typically people will in this case will use the central one, which is you use you know, a point here. You try to get the partial derivative at this point, and that partial derivative is basically the f at this point minus the f at this point divided by 2 delta s to get you the partial derivative value at this point here. It's called a central way. Okay, delta t is really for each time point is the f of the, you know, time to the left, the time to the right minus the time to the left divided by delta t. So it will be an f value here minus f value here divided by delta t will give us the partial derivative with respect to time at this point. And the second partial is really you have the difference between the first partial, one calculated with the forward, one calculated with the backward approach. You take the difference and take the delta t. Okay, so it's the change of the partial derivatives, change of time. Sorry, not the change of time, change of the stock price. Now, actually, if we really look at this, it's this, say, pick a point ij here, pick a point. So say pick this point. The second partial is calculated on the partial derivative here of this minus that, f I plus 1 minus f at the so if you call this the ij point, so you're getting one estimate of the partial derivative by f I j plus 1 minus f ij divided by delta s, which is this one here. And the other one is also a, it's calculated from this fij minus fij minus 1 divided by delta s. Now, the first one is the partial derivative at this point. The second one is the partial derivative at this point. Then you divide it by delta s. Okay, so then it gives you the partial derivatives. So the difference of the two partial derivatives and divided by delta s give you the second partial. So from the formula here, you may looks like this is the forward and this is the backward and divided by delta s, but essentially they're actually the two forward because they are the partial derivatives at two different points. Okay, this is the forward at one point, this is the forward of the point that is lower than that. And you basically rearrange that, you will get this number here. Okay, so you get your second partial derivatives. Now you get everything. So you just plug in the partial derivative to calculate, right? So into that partial differential equation there. And so what you see here is you have your each S is basically J times delta S. That gives you the actual S. And time T is really I times delta T, okay? So if you are at time index I and the stock index J for the state variable. Now they all have a whole bunch of once you put in, you have a whole bunch of delta S that you can cancel out. So you and then end up with this equation here from here. Now I basically color coded this equation here, this one here, and I then take, you can take common factors out of that. For factors for fi j minus 1, you will have this in front of them. And you can do that for fij, fij plus 1, and fi plus 1j, okay? And once you have done that, you can get rid of those delta t's at the denominator by multiplying delta t at both sides of the equation. Okay, then you will have this. Essentially, you minus delta t so that this part become a positive number here. So you get an equation like this. So for those terms in the square bracket, they're just some numbers that you can calculate because you know all those things. You know which node you are at. You are at some j's, right? And you have some I and j for that particular node. You can calculate this number here because you know the delta t, you know j, you know sigma. They're all given to you. You know r, you know q. So all these numbers are given to you. So you can calculate those numbers in the bracket. So let's just call them a aj is this, bj is equal to this thing here, cj is equal to that. And to write it in a more compact way, aj times fij minus 1 plus bj times fij plus cj times fij plus 1 is equal to fi plus 1j. Okay, so basically this equation linked 3 nodes to 1 node. What are the 3 nodes? So those 3 nodes are ij minus 1, ij plus 1. So they're all at the I point. So j plus 1, j, and j minus 1. Related to the one where you have the same with the I plus 1, which is actually one step later, but it's at j point. So essentially, you're linking those 3 points with this point. Okay, so there'll be, say this is ij, so this will be ij plus 1, this will be ij minus 1, this will be I plus 1j. So the value at those 3 points is linked with the value here. And this is true for every single numbers here. So you get, this is one set of equation. This blue one, the black one is that side of equation. The blue one is that side of equation. The orange one is another set of equations. And then let's take a look at the boundary conditions. And then we'll look at how many sets of this simultaneously as how many sets of this equation that we have. Okay, what are the boundary conditions? Well, for European put that we have in this particular example, we know the maturity value, right? So we have this K minus S, the max of K minus S or 0 is the payoff. And S at any node is basically J times delta S, right? So we're at the maturity time, and the S for node J is J times delta S. K minus that is positive, is this number is negative 0. So this give us the payoff of the put at maturity n, when I equal to n. Then at the node, the vertical node is J. So we know all those numbers. So we basically know every number along this line here. And we also know that Fi 0, well, Fi 0 is basically this line here. And at this line, the stock price is 0. So we know the value of the payoff at this point is, if it's European, is really K here. And all of those points are really the present value of K. And by design, we know S max is greater than K. So we also know this line, because this line is S max, and S max is a very large stock price, which by definition is going to be, by design, it's going to be greater than K. So the price of the option of this put must be 0 along here. Okay, so actually for this particular part here, Fi not equal to K, not for all the i's for European. If the European is K only for the last point, and for the points before that, they're all equal to the present value of the K at that point. But for American, this is for American option, this is true. Okay, so this is not strictly true for European. It's true for American. And for European, you will have, this is K, this is K discounted for 1 period, this is K discounted for 2 periods, and so on. So we know those value that I highlighted here in blue. So every single point. So if we will look at it, you will then see that we actually have we actually have m minus 1, sorry, we actually have m minus 1 simultaneous equations. Why that's the case? Because if you look at the grid here, we have m plus 1 points, and from this, and all the way up to this will be linked to the 3 points before them. And this point and this points are not linked because we don't have a point here. We don't know what the point here is. We don't have a point here. So we have m plus 1 minus 2 points. So we have m minus 1 sets of equations. Okay. So we have m minus 1 set of simultaneous equations, then we can solve for m-1 unknowns. And these unknowns are the f values one time step earlier. So it's basically, out of those ones, we can solve the f value here, 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 all the way to here. Since we know this and we know that, so essentially we have the entire line. So out of this boundary condition, we can get the entire line here. And then because we know the value, the f value on this line here, we can then do the same thing through another set of m-1 equation, simultaneous equations. We can then get all the f values here as well. Now we can do the same thing all the way back to get all the numbers here. Okay, and all the f value when s is at any point here. Now, one of these points here is our starting point, or the current realized stock price. Let's say this is the price. Then the f values at this point is the current price of the derivative asset. And we use the put, then it will be the current value of a particular put. Now, if we have an American put instead of a European put, what we can do here is that we will also know the immediate exercise value. So here we can calculate on the final boundary condition here, the value of those points, right? Which is basically the expected value. Then we can also calculate the immediate exercise value. So if the immediate exercise value is greater, then we, instead of taking the solution out of these three, the simultaneous equations, and at this point we'll take the immediate exercise value as the value of f. And in that case, we'll get a set of f values here. Now for European, you don't do this. You just take the solution from the set of simultaneous equations. You will get these m-1 f's, and you just move forward the same fashion. But if you have American option, you can then compare the immediate exercise versus the value you calculated from the equations, and then put in the bigger one, and then you move one step backward again and repeat the same process. And if you do that, you will get the price of the American option. So that's in a nutshell the implicit finite difference method to solve numerically of a partial differential equation to price option. Now, what's the advantage and disadvantages? Well, for implicit finite difference method, if we have small enough grid points, so we have large enough a number of i's and number of j's, we can always converge to the true value. Okay, so it will shrink things enough. Computationally, the finite difference method is relatively expensive because you have, for each line here, for each step, you have to solve a whole bunch of simultaneous equations. So you have, a m-1 set of equations you have to solve simultaneously, which is quite expensive to do numerically. So it's computationally more involved That is a drawback. The advantage is the guarantee of convergence. You can shrink the steps. Okay, now let's move on to another approach for finite difference. It's called the explicit finite difference method.